All right, the chain rule. So this is going to be one of our tools in our toolbox, right? We have the product rule, we have the quotient rule, and now we're going to have the chain rule. And the chain rule is going to be used when we're trying to find the derivative of a composition of functions. Sometimes there's a workaround that you can do algebraically with your composition of functions, right? So if I had something like this, where I had f of x equals negative 4x plus 7 and g of x equals 3x minus 5, and I'm trying to find the derivative of the composition of their functions, I can do this without the chain rule. This gets a little trickier when I cannot manipulate my functions, but for right now, let's try to do it without the chain rule and see if we notice anything. So what I can do is I can take g of x and I can actually just plug it in to f of x. So I can take that g of x, c of x equals f of g of x, right? I can take that g of x, which is 3x minus 5, which I got from right here, and I can plug it in to f of x, right? And then I can just do some quick algebra, some quick maths, like they say in Britain, and I can get this, and I can find its derivative real quick by doing the power rule, and I get c prime of x equaling negative 12. Now you'll notice the derivative of f of x is negative 4, and the derivative of g of x, just the slope, is going to be 3. So you'll notice that that derivative of just taking those two and multiplying them together is equal to the derivative of their composition. So that's going to be kind of helpful moving on, right? Again, sometimes it works, sometimes it doesn't, as far as manipulating your equations. Here's an example of another one real quick, right? So let's say c of x equals sine of 2x. So this would be really hard for me to do because I don't really know my identities very well. I know one identity, and the double angle identity is not one of them, right? I'm sure you're kind of the same way. So once you learn the chain rule here, this will be a little bit easier. But you can actually do this one without the chain rule if you know this double angle identity, right? So we're going to write c as a basic function, and then we're going to use that to find out what c prime is real quick. So the double angle identity of sine is sine of 2x, so your double angle there, 2x, equals 2 times sine x times cosine x. And then what we can do is we can find the derivative of that by doing the product rule, right? So when I do the product rule, I do the first times derivative of the second, plus the second times derivative of the first, so on and so forth, right? And now, let me move, oh, I hope you can see that. I think you can. Might have to pause for a second. There we go. You'll notice I have two sines and two cosines going on there, right? So I can simplify that. And now, sidebar, plot twist, right? We know that the cosine of 2x, the double angle for the cosine of 2x, is just cosine of x, cosine squared x minus sine squared x. So we can replace this right here with this right here, and that's what we're going to do. So c prime of x equals 2 cosine of 2x. Yeah, so let's flesh that out, right? So basically we had c of x equals sine of 2x, and we just found that c prime of x equals 2 times the cosine of 2x. And you'll notice, again, let's let g of x equal 2x, so that's the inner function, and let's let f of x equal the outer function, sine of x. You'll notice that the derivative of the first part here is 2, and the derivative of the second part here is cosine x, right? So then we can see that, okay, that means that c prime of x equals 2 cosine 2x. It's the derivative of the inside times the derivative of the outside. Make sure that you leave that g of x alone, right? It's derivative of the outside times the derivative of the inside. Chain rule. If that was a little tough for you, don't worry, because we have these things right here. I don't know if you guys have seen these before, Russian nesting dolls, right? But basically, oh, this is a good little picture here, right? This is cute. Basically, these are just little Russian nesting dolls, little functions, right? You have the big outer function, and then inside of those, you could put all these little functions. basically what you need to do is you need to take the derivative of the little guy times the rest of it, then the derivative of the big guy, then you kind of work your way down, right? So mathematically, I guess this is how you'd say it, the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function c defined by c of x equals f of g of x is differentiable at x, and c prime of x equals g prime of x times f prime of g of x. Basically what that's saying, I'll move my little picture here, the derivative of the inner function times the derivative of the outer function evaluated at the inner function. The derivative of the inner function times the derivative of the outer function evaluated at the inner function. So let's do a quick example. I wonder if my picture is going to get in the way again. Let's say I have r of x equals the tangent of x squared. And I want to find this derivative. I don't know any crazy trig identities that'll help me with this. But I can say that the inner function is going to be this tangent of x. And the outer function is going to be the whole thing squared. So can you imagine x squared being the outer function and the inner function being the tangent of x? So if we say f of x equals x squared, we can find, and g of x equals the tangent of x. We can find f prime of x easily, 2x. We can find g prime of x easily, right? Especially if you have your little note sheet with you, secant squared x. And now what we can do is we can piece those two together. So f prime of g of x is 2 tangent x, right? It's basically I replace x with whatever the inner function was, tangent of x. So r prime, the final everything put together, is going to be the derivative of the inside times the derivative of the outside evaluated at that function, right? So it's going to be secant squared x, which I found by doing the derivative of the inside times the derivative of the outside, 2 tangent x, right? And eventually, if you're getting bogged down with the notation, eventually you'll just say, okay, the derivative of the inside times the derivative of the outside. Notice this is a multiplication symbol, not an addition symbol. We can make these kind of tricky here. Like this, you'll never see, r of x, you'll never see it written like this. You'll always see it written like this. You have to remember that tangent of x is going to be the inner function, and the squared actually goes on the outside like we did here. This is a much easier notation to use, but for some reason this is the notation that you always see, right? So same thing here. We could have cosine to the 4th of x, right? So that's going to be cosine of x to the 4th. The inner function is going to be cosine of x, and the outer function is going to be x to the 4th. Same thing here. The inner function sine of x, the outer function to the 5th. The inner function secant of x, the outer function is going to be x squared. Outer is going to always be the power. The inner function is always going to be the trig function, right? So brass tacks, bottom line stuff, when you're doing a chain rule, when you're trying to find the derivative of a composite function, you do the derivative of the inside times the derivative of the outside. If you can remember that, you'll be in good shape. All right, peace.